All right, recording is started. So, welcome to today's Thursday, January 13th. These are the problems I assigned to you guys come off a page that looks like this. So chapter 14, chapter 15. I'm going to do as many of these as I can with you guys today, which is actually going to be most of them. I'm going to get real close to finishing these. Before we do that, though, I've got a couple of demos for you guys. So let me switch my screen over. And we're going to start with Rubens tube. So this guy's going to light a line of flames. It's like, imagine that being like 100 candle flames or something like that, right? He's going to play a sound over that. Right, let's hear.
449 hertz frequencies.
Ooh, he said 449 hertz frequency, right? That sort of matches like some musical note. I don't think it's exactly one of the notes, but I think it's a little bit above one of the A notes, because I know one of the A's is defined as 440. But maybe that just does turn out well for these particular candle flames. Now, yeah, look at this. It sets up like a standing wave type pattern, right? Now, you guys know that sound is a. Oh, wait, let me back up a little bit. I want to talk about timbre. So you guys hear like the quality of this sound? It's like very flat, very computer sounding. It's like. What's something that distinguishes different musical instruments? Like if you played that note on a guitar versus a piano versus a French horn, like you would know that, okay, those are like different kinds of instruments. So the musical term for that is called timbre. The physics of that has to do with overtones. So when you play a certain musical note, there's a dominant frequency that's associated with that, but there are also a bunch of harmonics that play along with that. And the harmonics, those overtones are different for different instruments, and that's what gives each instrument its own unique timbre. Right, so back to thinking about how the sound wave would work. You guys know that sound is a longitudinal wave. It's a pressure wave, right? So sound moves through the air. The air gets more and less pressurized. And this line of flames, it looks like a classic transverse wave, doesn't it? It goes like up, down, up, down, up, down. But think about what's actually causing that is that there's some air above it that has changing pressures. So this point right here, is this going to be a high pressure or a low pressure point? What do you think is pushing those flames down? It's got to be like a high pressure point, right? Okay, so I see it's oscillating. So we've got low pressure, low, high, low, high, low, high pressures. What about later on? It's going to change the tone. So maybe go later on here. Right. Let's listen to these. You guys hear that tone going up? So that is increasing frequency. Remember, each frequency is associated with a certain musical tone. So I'm looking for, here we go. So for the video, I'm gonna throw up here a poster here. I pointed out in class one hanging from the ceiling. It's this one right over here. You guys see speed is equal to wavelength times frequency. Okay. So speed equals wavelength times frequency. Now the speed of sound is whatever it is. It's like 340 something meters per second. But you guys heard the musical note changing. That's to say the frequency was going up, 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 up. So higher pitches, like higher frequencies, like do, are associated with a higher frequency number. So for example, look at the 400 to 500 to 600 hertz. I'm just making up numbers, but guess what they do. And what would wavelength have to do in response to an increasing frequency to have a constant speed of sound? Because the speed of sound is not changing. It's just like 340 something meters per second. So larger and larger frequencies, you would need a smaller and smaller wavelength. And that's exactly what you see right here with this Rubens tube. Remember, originally it was like 4 loops, and now we're looking at like 6 loops, something like that. That might correspond to what you're looking at is maybe like 3 wavelengths, right? Remember, every 2 loops is like a wavelength, something like that. Okay, so there you go. There's a Rubens tube. Actually, I got another Rubens tube. Let's take a look at this one. So there you go, get some sound visualization. And one of the problems that we're going to cover today involves a pendulum swinging from the ceiling of a very tall building, maybe something kind of like a folk call pendulum. And I thought I'd told you guys about this in fall semester, but my students earlier today have been telling me that I have not. So I'll go ahead and cover this here because it's going to be relevant to what we're talking about today anyway. Now this one, I took a picture at University of Central Florida. So if you go there, find I think it's one of the science buildings or physics building, you might be able to see this. This is hanging in a stairwell. It's a really, really long pendulum, really long pendulum. Actually, it's supposed to be a Foucault pendulum. Oh, I think it's what it says right here, Foucault pendulum. The idea is that it swings back and forth, and it appears to change its orientation over the course of the day. Let's see. Sorry, if I have the folder ready to go. Let me dig this up from my files. There we go. So let's look at the video of this thing on. So this is probably in some science museum or something, or maybe university, I don't know. Okay. But this pendulum's just swinging back and forth. But do you guys see these pegs that, there's a bunch of them that have been knocked over. Okay. So it looks like over the course of the day, this thing is actually, well, it appears to be changing its orientation. I'll tell you guys the point of this though, is that actually it is not. The pendulum itself is just swinging back and forth. That's all it's doing all day. Okay. But over time, it looks like it's changing relative to the Earth. Let me forward to the end of this. Okay. So let's see, does it knock it down? Ooh, guess I'll tap it right there. I think it's this next swing that does it. Let's see if it does. This next swing knocks it down. Okay. But there's some time period that's associated with that swing back and forth. I bet you could use that to, there it goes. I calculate the length of that, which is kind of like your guys' last lab. That's sort of the tie-in to what we're doing here today. Here's a time lapse on that. That's what this looks like. Okay. The point of this is that it shows that this is evidence that the Earth is rotating, because really what's going on is the Earth is rotating underneath it, and the pendulum is just going straight back and forth all day. So Foucault pendulum. And this particular video, you can tell that this is in the northern hemisphere because it has a clockwise type motion to it. See, if you set up one of these in Australia, it would look like it was going counterclockwise over the course of the day. This one's going clockwise, so it has to be northern hemisphere. But depending on your latitude, this works more or less effectively. What do you guys think on the North Pole? Do you think this would be super effective or super boring? I'm thinking it'd be really effective on the North Pole, because North Pole, the entire Earth would spin under it once every day. So it would go through one complete cycle every day. Versus if you put a Foucault pendulum, say in Ecuador, like which is right on the equator, that would be like the world's most boring Foucault pendulum, because you wouldn't see it change its orientation at all. It would just go back and forth all day. So that'd be kind of boring, but maybe a good science experiment just to show that it wasn't working. So your latitude's close to the equator, not very much effect. The closer you get to the poles, the better this works, and then it reverses direction depending on your hemisphere. All right, so there you go. That's showing the screen. Flip back over. Okay, so let's do some of these problems. Actually, we should get through most of these today. Remember, the due date on these isn't for like another week, so there'll be like plenty ahead of time. All right, we're doing chapter 14. Oh, hold on a minute. Where did? Hang on. Make sure I didn't misplace the paper here. All right. First question. Oh, it looks like we got a bunch of apples hanging from a spring. So the spring stretches by so many meters when apples of this weight are suspended from it, as shown in this figure. What is the spring constant of the spring? Oh, actually, you guys know how to do this one already. This is Hooke's law. You guys remember Hooke's law? F equals kx? That's exactly what this is. Because the weight of the apples is a force. The amount of stretches is x, displacement from the equilibrium position. Okay? And the question is, how stiff is the spring? What's the spring constant? So it's going to go F equals kx. Remember, this is Hooke's law. Okay. Let me draw this real fast just to remind you guys, just in case you're exactly 100% following. I'll draw one horizontal, they did vertical, but that doesn't really matter. Let's say I had some spring that was unstretched and uncompressed, had some natural length. And then you put a force on this thing that stretches it by some amount. Say the amount it stretches is like X, because you put a force on it. Like there's some F force, and the spring's pulling back the other way with an equal and opposite force, Newton's third law. So what's the magnitude of that force? Oh, K times X, where K is the spring constant of the spring. I'll stick with this. So let's do that. They told you the weight of the apples. I'm going to make up my own number. Maybe it's like 5 newtons. Okay. They did 3.2. I'll do 5. And we're trying to solve for K. I'll step to that spring. And let's say it stretches 0.20 meters. Just making up numbers. Okay. They could give you how many meters. That was nice. They could have said centimeters and made you convert, but they gave you meters. So, but one algebra step, just divide over the meters. So 5 over 0.2 in this case. So my spring constant in the notes is like this many newtons per meter. That's the stiffness of the spring. Like that. So if I had like 5 apples hanging from a spring and it stretches 20 centimeters, I think, my spring is that stiff. Number 71, how much potential energy is stored in a spring with some given spring constant if it's stretched by some amount? Energy. Okay. So the first question was Hooke's law, F equals Kx. And this question is how much energy is that associated with? You know, actually, I'm going to glance forward to the next question because this ties the two together. You guys see the next question has a nice graph for you guys, F versus X. And hey, look at that. That's like F equals Kx, kind of like Y equals MX. So the force associated with stretching some amount, the more you stretch it, the more to the right you move on the graph. The force is how far up, like that coordinate. And the question we're trying to answer right now is energy, how much energy is stored. Wouldn't that be, do you guys remember what property of F versus X graph tells you how much energy is stored in the graph? Sorry, stored in the spring? Isn't energy force times distance, or work is force times distance? Somebody do that? Okay. Some kind of force times some kind of distance, okay. But it is a variable force. It ends up being the area of this triangle, the area under the curve. Okay. You guys might remember that from a few months ago. Okay. So that's what you could do that here, or you could think of it this way. Okay. If this is X and this is Kx, right? X wide and Kx tall, and you want the area of a triangle, which is 1/2 base height, wouldn't that be 1/2 times X times Kx, which is called 1/2 Kx squared. And that is the formula for energy stored in a spring, 1/2 Kx squared. Okay. So the force is Kx, and the energy is 1/2 Kx squared. Okay. So let's apply that right here. How much potential energy if they told you the spring constant? Actually, I'm going to use my numbers from last problem. So I got 25 Newton per meter, so I'll just go ahead and use that number, 25 Newton per meter. And the stretch amount, I'll use the same stretch amount as before too. So this many meters. And don't forget to square the stretch amount because it's 1/2 Kx squared. So 1/2 Kx squared. Okay. This is, well, here's the number. Okay. And what's the unit on that? That's 0.5 what? Is it kilograms, newtons, joules, watts? What is that? How do you measure energy? Joules, yeah, it's 0.5 joules. Yeah. $73. We've got a force versus length graph. I was just referring to this, so this we're looking at force versus distance. So here's physically what's going on. We've got a spring, we're stretching it, apply more and more and more force, it stretches more and more and more, and that's a direct relationship. So 2 questions. What is the spring constant of the spring? And the follow-up question is how much energy is stored in the spring? So saying you have to figure out what property of the graph would apply to that. Let's say you guys go to college and you go on some like math or science track and you have to do graph interpretation. One of the things I want you guys to be able to get out of this class is, well, what properties could you get off a graph? And this is a pretty information-rich graph if you know what to look for. So each y coordinate tells you the force. The slope tells you how stiff the spring is because F equals kx, that's like y equals nx. And the area under the curve represents the energy stored in the spring, which also represents the work that you did stretching it to get there in the first place. And so let's do that. Part A, what is the spring constant? Well, spring constant would be the slope of this curve. Actually, I'll just go ahead and use their numbers for this one. So like rise over run. So K is equal to, let's say, if you apply a force of this many newtons, then it will stretch by this many meters. So K is equal to this many Newton per meter. What's that? Part B said how much energy would be stored in the spring. So it could apply 1/2 kx squared to be perfectly fine. You could also say the area of the triangle. So that'd be 1/2 base height. So the base, okay, when stretched specifically this much, right, this much. Okay, so like 0.5 meters. So the base would be this many meters. And the height of the triangle, which is the force to get up there, looks like that many newtons. So this many newtons. Okay. 1/2 base height area of the triangle. That's looking like the energy stored in the spring is this many joules. How many joules right there? Oh, yeah. Okay. Number 74. How long should a pendulum be to have a time period of, say, this many seconds on the moon where the gravity field is really weak? Okay, that's interesting. This is definitely related to the last lab that you guys did. You guys figured out an expression for time period of a pendulum based on its length. Remember the mass of the bob and the starting angle at the end of the not mattering. Now they're doing an interesting twist here. We're taking this to the moon, but you guys know it's going to be something to do with that time period of a pendulum formula. Time period of a pendulum is 2 pi times the square root of length of the pendulum divided by the gravity field. Okay. That was the answer to your guys' last lab. Okay. Remember where pendulum, okay, all the masses in the bob, it doesn't matter what the mass is, just as long as it's all located there. Here's the length of the pendulum. Okay. The time is to swing back and forth once. How much time? Okay. So they're asking how long does the pendulum have to be? If you know the gravity field and you also timed it. Okay. Pause here. There's I think 3 different stories you can do just as a basic algebra of class. Okay. If you know the length of the pendulum and the gravity field, you could predict how much time it takes to swing back and forth. Right? Or you could do what we're doing here, which is if you know the gravity field and the time, you can back calculate how long the pendulum had to have been. Right? Or the third story they could have gone with is suppose you're hopping planets and you arrive on some planet. And you're like, I wonder what the gravity field is on this planet. So you break out a pendulum of some known length, or very easy to measure. You break out a stopwatch, just let it swing back and forth. You can back calculate the gravity field. Right? That's not what we're doing here, but they could have asked that question. That would have been a good question. Now you could solve this in terms of variables, but I'll go ahead and plug in the numbers first. I'll make up my own numbers though. What if the time period was like 5 seconds? It takes 5 seconds to swing back and forth. Let's just hop on the moon, real slow. I bet that had to have been a really long pendulum to do that. Hey, maybe kind of like that football pendulum, right? Where it's just like super long. 2 pi times the square root of the length that we're solving for, 5a. I'll go ahead and use moon gravity, 1.6 meters per second squared. The giant square root right there. Right, so now we'll do the algebra part, which is just unvarying that L. We're going to solve for L, do a series of steps and solve for that. So first step, divide both sides by 2 pi. So 5 divided by, let me do something that's wrong. Okay. You guys see that right there? Okay. Is that the correct next step, or did I do something wrong?
Oh, it's not correct, because you can put parentheses right for 2 pi.
Yeah, you guys hear Joshua? Yeah, you guys catch that? Okay, yeah, I think Matthew's, don't you guys see that? See, the way I type this, I'm just saying this because sometimes I'll say students do this. Okay. The way the calculator is interpreting what I typed is it's doing 5 divided by 2, and it stops dividing, it turns around, multiplies by pi. No, that's not what I want. I want to do, and I got 7 point something. I want to do 5 divided by open parenthesis 2 pi like that. And that gives you this number, which is, okay, that's what we're looking for. So divide the 2 pi down, get this many, well, I guess that would still be seconds, is equal to the square root. Okay. All right, next step is square both sides. So go ahead and square. So L on 1.6 second squared is 0.6 something something. I guess that would be square seconds, right? Okay. Then if you multiply up the gravity field, notice, the square seconds is going to cancel out. It'll leave you with meters, which is going to represent the length. Right, awesome. Yeah, did do this right. It's 1.6. The length of that pendulum then had to have been, like this many meters. I just made it random numbers from scratch, but kind of interesting it turned out that way. It ended up being like almost exactly a meter. I'll go back to the beginning and just double check my answer. So it is 2 pi times the square root of 1.01 meters divided by 1.6 meters per second squared. Yep, that's about 5 seconds. Okay, so it all checks out. Of course, my numbers are different than the book numbers, like I normally do these notes. But that's how you solve that.
Mr. Griffin,
Yeah.
how do you double check it again?
Oh, okay. Yeah, just take your answer. Yeah, it's a great question. Plug it back up into here.
Oh, okay.
Right? And then plug in 1.6 meters per second squared for the moon. And you should get your time value, time period. Okay? So like that. Number 76, ocean waves. So an ocean wave has a length of so many meters. A wave passes a fixed location every so many seconds. What's the speed of the wave? Right. So fast way to do this is look at units. We're looking for speed, which is meters per second. Do meters divide by seconds. So you can probably solve it really fast like that. I'm gonna solve it a little bit longer way just because it connects to a formula for like a wave formula for you guys. Actually, this was a story I told you guys too the other day. Is what if you're like sitting on a dock and maybe there's like a post out here, right, sitting on this dock, and you're watching the waves crash. It goes like crest, like it's bobbing up and down. Okay? And you're able to get some measurements. So you know the let's say the crest to crest distance, the center to center distance. So you either measure that or somehow you determine that to be, I'm going to make up my own number. I'll call this like 10 meters, a little bit different than the book. And you break out a stopwatch, I'll call it lambda for wavelength. And the time it takes to get there is, I'm just going to make up a number, let's say at 4 seconds. Okay, well, there must have been some associated wave speed to get there. Now, of course, the quick way to do it is 10 over 4 would be 2.5. That's probably the answer. But there's a wave formula I told you guys, which is speed of a wave is equal to wavelength times frequency. Okay? You guys remember how frequency is 1 over time period? So if it took 4 seconds to go from crest to crest, the frequency is 1 over that. So frequency is 1 over the time period, which is equal to, well, 1 over 4, a fourth of a hertz. That's 0.25 hertz, right? Isn't that? Okay. So if I plug those in, I got 10 meters with a frequency of 0.25 hertz. Remember, hertz is 1 over seconds. That's like meters per second, which gives you speed. That's still 2.5 though, 2.5 meters per second. Check my notes numbers. That's it. Next one, number 81, speed of sound in water is, okay, they're giving this book value, they're saying 1498 meters per second. Well, a lot of caveats on that. Are we talking about fresh water or salt water? What temperature are we talking about? So okay, they go to the number. A sonar signal is sent straight down from a ship to a point just below or sorry, at a point just below the water surface. And so many seconds later, a reflected signal is detected. How deep is the water? Well, we got a speed that the sound moves through the water, and we got a time, and we're looking for a distance. Oh, well, distance is equal to speed times time, right? It might be that straightforward. This one, it's better if you draw it out because there is a critical thinking step you have to consider here. So number 81. So here's the ocean surface, got ourselves a boat, and way deep down is the ocean floor. We're up here in this boat, we're gonna send a signal down, it's gonna boing, bounce off the ocean floor and come right back up to us, okay? Well, if it took some time to go from the boat back to the boat again, like an echo, this is an echo, right? Then isn't what we're solving for this distance, x, like the ocean depth, didn't actually travel that twice, right? Once down and the second time back up. Okay? So you can do distance equals speed times time, but the distance that the sound travels is actually 2 times the distance you're interested in, because it's 2 times the ocean depth, right? Once down, once up. So this is what we're applying right here. Okay? Distance equals speed times time. We're interested in, okay. Is that fair? Right, so they told you the speed of sound in water. I'm going to round that up a little bit to call it an even 1,500 meters per second. And I'm going to make up my own time. Let's say it took like 3 seconds, like that. I wonder how deep the ocean is under my boat. Well, just multiply speed times time and then divide by 2. So what is 1,500 times 3 all divided by 2? That's going to look like this many meters. Hey, in my notes, how many kilometers is that equal to? You guys thinking 2.25 kilometers? 2.25 over 1.6 something. Okay. That's almost a mile and a half deep. 2.25 kilometers. Ooh, 84. It's a good one. You guys remember those interference pulses you guys saw? So I played you guys some demos that look like these. Got a couple of wave pulses that are going to interfere with each other. You guys remember there was like, no, the wave pulses I showed you in the demos were, they looked more like sine curve waves looking like, right? Like bell curves. This is more like blocky, but that's okay. It's going to work the same way. If it was like 10 centimeters and 10 centimeters, when they cross over each other, remember it made like a giant 20 centimeter? You guys remember that? Okay. Right. So what does it say? We got sketch the result for each of the 3 cases shown below, where the centers of the 2 approaching wave pulses lie on the dashed line, so that the pulses exactly overlap. So like the center of this pulse and the center of this pulse exactly overlap, and so on. So this is really 3 different problems, right? Going to do each one individually. Number 84. I know your book labeled them 1, 2, and 3. Maybe I'll call it like A, B, and C, because that's really what's going on. Like part A, part B, part C. So the first one, let's see, there's like the dashed line. Right? There's, see, wave pulse here, wave pulse here. They're moving toward each other. Okay. And they're going to meet probably at the center to center to point. They're going to meet like right there. Okay. So when they do, what's that going to look like? And so there's the before picture. There's the picture right when they're crossing over each other. I'm thinking it's going to look something like this, right? Or if that's 10 centimeters and that's 10 centimeters, that would be 20. Okay. I bet you guys know what's going to happen even after that, which your book isn't really asking for, but we can go an extra step. Okay. Do you guys think that the pulses will look something kind of like this? Where now this one's continuing on this way, this one's continuing on this way, like that, right here. So your book was just looking for that middle picture though, so that would be the answer. Yeah, is that all right? Okay. How about the other 2, like part B? Part B, we got a positive pulse and a negative pulse. One up and one down, like positive 10 centimeters and negative 10 centimeters. Actually, this one I pretty much also exactly played for you guys in a video demo. You guys know what happens with this? So we do the same thing. I'll get those three reference lines going. So before, during, and after the pulses pass each other. So before, it looks like we got one up pulse and one down pulse. Okay. This guy's moving this way. This guy's moving this way. Okay. They'll like meet in the middle. Okay. When they do meet in the middle, what's that look like? Do they exactly wash out, just cancel out? That's it. That's the answer. Positive 10, negative 10 cancel out. That's called destructive interference. You guys remember destructive interference? Okay. Is that the whole story? Like, what if you looked at like a second later? Does it just flatten out forever? Oh yeah, yeah. So after this frame, you guys remember they just like sort of just pass through each other and just keep on going? Okay. So the next frame would actually be kind of interesting, right? I think really interesting. It looks like this, and this guy keeps going this way. This guy keeps going this way. So they do cancel out for an instant, but then they just keep on going. Pass this straight through each other. Guys good so far? And then let's gotta check the video, make sure these are showing up on the video too. Have a new camera positioned a little bit different. Okay, so there's a part C that got like 10 centimeters up and 20 centimeters down. I bet you guys have caught on by this point how this is going to look. So let me get three reference lines before, during, and after the wave pulses pass each other. So it started out as like positive 10 centimeters and negative 20 centimeters. I'm making up the numbers, but you guys get the idea. Okay. This guy's traveling this way. This guy's traveling this way. Okay. When they pass over each other, well, what's positive 10 plus negative 20? That'd just be like negative 10. So it's going to look like that. Okay. That's the answer the book is looking for. Okay. But you guys know more of the story. You could go another step and say, well, after they pass each other, this guy's going to go like this and keep on going this way. And this guy's going to keep on going this way. There you go. Sorry, I messed up the last one. Like this. Okay. That's good. There's a pretty similar one that's a bit more challenging though. You guys see number 87? Number 87 I assigned you guys as a bonus problem. So it's the exact same principle, but it involves like triangle shapes instead of rectangle shapes. The demos that play for you, of course, have like curvy type shapes. So yeah, if you want a good challenge question based on what we just did, then see if you can tackle that one. Right, so that's all the main homework problems I assigned from chapter 14. Let's take a look at these chapter 15 questions. So number 66, sonar. Got a ship surveying the ocean bottom. Some sonar waves straight down into the seawater from the surface. Oh, hey, we just did a problem that was very similar to this, didn't we? Right, now this one's a little trickier. There's an extra step you have to throw in, but we did do one that was pretty similar to this. Ship bouncing sonar waves off the floor. Okay, so here's the figure for this. The first reflection, which is bouncing off the mud from the seafloor, returns after this time interval right here, 1.74 seconds. But then there's a second reflection because there's part of the signal actually goes into the mud and bounces off the bedrock that's actually below the mud, and then that signal gets reflected. And that of course takes more time, about 2.7 seconds. The temperature of the seawater is 25 degrees Celsius, and the speed of sound in mud is 1875 meters per second. How deep is the water and how thick is that mud layer? Okay, now they told you the speed of sound specifically in mud. You guys know the speed of sound in air is about 340 meters per second, depending on the temperature. Okay, so mud is going faster. You know what, they never told us the speed of sound in water, but they did in an earlier problem, it was like 1,500 meters per second, pretty close to. They told you the temperature of the water, which might be a hint they want to send you on an Easter egg hunt. So that's what we're gonna do. And I did that ahead of time for you guys. In your book on page 405, they tell you speed of sound in various media, this table. And water at 25 degrees, they're calling 1493. Okay, earlier in the notes, I did 1500. Actually, you know what? Here's seawater. Actually, I should use the seawater number, shouldn't I? Yeah, it does say seawater. Let's do that one. 1533 then, meters per second for seawater. All right, so kind of an extended version of one that we did earlier. Gonna go 60s. Gonna redraw this. All right, we got the ocean surface. Got ourselves a ship up here. All right. There's the mud floor, and then beneath that is the bedrock. One signal goes up one, and the other signal goes through the water, then probably speeds up through the mud. Yeah, and then goes back to the mud, and then back to the water, back to the ship. So two different things going on. You guys know from before, it's something to do with distance equals speed times time. Right? All right. Whatever the time is associated with the round trip. So whatever distance x is, it's really 2x to align with whatever time for the round trip. Okay? So let's start with the water and say through the water, remember it was going 1533 meters per second. Okay? I'll make up the time. Let's say it's like 2 seconds even, 2 seconds exactly. Okay? Now that's 2 times x. So you do have to divide both sides by 2. Okay? Oh, actually, you can do that in my head. Don't need to calculate for that. That would be this many meters deep. Okay? So that would be the water. We'll do like sub W, like depth of the water, something like that. Okay? How about that mud layer though? Maybe this is x sub W, and then this could be like x sub M, like for the mud. Okay. How deep is that that mud layer? Well, it's going to be. Maybe I could just look at this part right here and say like, well, that reflects, right? So there's some distance we're solving for. There's some speed through the mud which was given, and there's some time associated with that reflection. And that's the first part we're going to have to deal with. So 2 times x mud is equal to speed through the mud times. And now here's the part where you have to apply some critical thinking. Remember, no, I did make up my own number. I said 2 seconds for the echo off the mud floor. So 2 seconds through the water, down and up. Okay. Let's say that this other reflected signal is like 3 seconds. Okay? Say 3 seconds. Because if this whole thing is 3 seconds, but you know 2 of those seconds involved going through the water, right? So maybe 1 second down, 1 second up through the water. How many seconds would be left for just the mud journey? 1. Yeah, if the whole thing is 3, so let's say x, or sorry, not x, t of the mud reflection is like 3 seconds. Right? You already know that 2 of those seconds were through the water, right? 1 down, 1 up. So the other, 3 minus 2, that's how you get 1. Okay. So I'm going to put 1 second in here. 1 second. Because the reported number is 3, but I'm subtracting off the time through the water, which was 2, that leaves me with 1 second. Okay? You guys able to do that with your book numbers? Some of them? Right. Now remember that is still a reflected time. That's still down and up through the mud. So I still have to divide both sides by 2. Okay? But this, or it should have said T, but the speed through the mud, I'll use the book number for that, which is 1875 meters per second. Okay. So 1 second, down and up again. Divide both sides by 2. I'm looking at the thickness of the mud is about this many meters. Yeah, we go back again. So what the book told you was, they told you two time values. They told you the time for the reflection off the seafloor, just the water, the signal going through the water. They said 1.74 seconds, and my notes I said 2 seconds. Okay, so that was pretty straightforward. You just plug that into this one. They also told you a reflection time off the bedrock. Now they said 2.36 seconds. I said 3 seconds. I rounded up a bit just for the notes. But remember that time is like maybe like a 4-part journey, right? Water, mud, reflected mud, and then water again to get back to the ship. Okay? But you already know the time associated with just the water part of the journey because that was given before. So you subtract the two. So if I take the total journey off the bedrock and subtract just the water part of the journey, you'll be left with the time involved with just through the mud. Okay? So my example numbers were, if the total time from here off the bedrock back to the ship was 3, and then the water part was 2, I did 3 minus 2 and got 1 second. Okay?
Where'd you get like the 1533 from?
That came from this table and book. So the speed of sound in seawater is 1533 meters per second at 25 degrees Celsius. Yeah, that was the part where the book did not, in that question, tell you that number, but they said 25-degree water, seawater. So you had to look that up. Then number 71, a vertical tube with a tap of the base is filled with water and the tuning fork vibrates over the mouth. As the water level is lowered, resonance is heard when the water level is dropped 17 centimeters, and then again after 49 centimeters. What is the frequency of the tuning fork? This is really similar to the next lab that we're going to do. So 71. We're going to draw this for you guys, and then no, the way we're going to do this lab is you'll know the frequency associated with the tuning fork, and we're going to solve for the speed of sound. This question is asking, if you know the speed of sound, can you back calculate what the tuning fork pipe has been? So we're going to have a PVC pipe. This is going to be our setup, which is pretty much this problem. There's going to be a tuning fork that you can hold over the opening. Okay. You strike this hand, it goes bing, some particular frequency, which is like a musical note. And this pipe is going to be submerged in water. And at some point, maybe the water level is like here. Okay. But you can move the pipe up and down, or the book said you can change the water level. Either way, it's the same idea. Maybe at some other point, the water level might be like down here. Okay. And as you raise or lower either the pipe or the water level, at certain points you'll hear resonance. So you strike the fork, it sounds like beep, but then you move the pipe up and down, and at some point, for some particular length, it'll sound like you guys will hear this next week when they break out the materials and we did this lab. It'll happen at specific intervals. So let's say that this is, I'll just go and use the book numbers for this. Let's say this is 17 centimeters, so that's like 0.17 meters. Okay? And the next distance that happened was at 49 centimeters or 0.49 meters, like that. Okay. Do you guys notice that what's 17 times 3? It's not 51. That's really close to that, isn't it? You see the ratio of these two distances is very close to a 3-to-1 ratio. Okay? Now, why would that be? That has to do with this right here. That there are certain places where you can set up these resonant frequencies. Oh, look at this. So a tube that's closed at one end, open at the other end. Hey, that's exactly what we have, except vertically oriented. That's the same idea, isn't it? Okay. There goes a quarter of a wavelength, then 3/4, 5/4. These are the harmonics that you can set up. The standing waves. Okay. So when you hear it resonate, it's like for some location like that's resonance being set up. And here's what the wave looks like. Now it's a longitudinal wave. So you got like a high pressure point here, okay, and then the kind of like spreads out. Okay. This gets closer to the tuning fork. Okay. And then when you drop the water level down, then this will still be a high pressure point, and then it'll be like a low pressure point, and it goes to high pressure point again. Okay. I just drew for you guys a longitudinal wave. and each dot represents like an air molecule. But you see, that was really hard to draw, and it's also really hard to interpret, right? That high pressure point, low pressure, high pressure, low pressure. Okay. So it's really common to represent longitudinal waves with transverse waves, even though it's not really what's going on. But I can draw it and then loop it over itself. That's what they did on that poster too. Okay, so it looks like that. Do you guys see that this distance here and here? There's a specific method we're going to do. It doesn't exactly end at the top of the pipe, so I'm trying to save a little time here. But you guys see that this is going to be the difference between 49 and 17 centimeters, 49 minus 17, which is 0.32 meters. Okay. Doesn't that correspond to half a wavelength? Isn't that half a wavelength right there? You guys see that? So if speed is equal to wavelength times frequency, and I know that this is half the wavelength, do you guys see that this full wavelength is going to be double that, which is 0.64 meters? You guys see it? And the speed of sound, I'm going to use this. I'm going to use 343 meters per second. It's probably pretty close to that. Hey, do you guys see that you could calculate the frequency of that tuning fork? So I've gone through a few steps at this point, but we're real close to the end of this problem. All I have to do algebraically is divide by the wavelength. 343 divided by 0.64 meters. I'm looking at a frequency of 536 hertz, which I Googled earlier, and I think that's pretty close to a C note. So maybe kind of close to middle C, I think. Okay. You guys got any questions? All right. Well, that's as far as I got earlier. Oh yeah, perfect time. Bell rings in 2 seconds. So you guys have a good Thursday, and we are pretty close to Martin Luther King weekend.